Have you ever seen like that one? It's like a, what do you call it? I guess a way of putting it is like a different denomination of string theory called supersymmetry string theory, I think. And you probably seen this clip, but it was a part of a on a panel, and Neil deGrasse Tyson was there, and one of the prominent mathematicians that was working on supersymmetry string theory was talking about how at the at the most cutting edge, at the most foundational level of like the mathematics for supersymmetry string theory, they found that math began to operate as a sort of error correcting code that is similar to the type of code that is found inside of like the internet when like so like there's not like a loss of information, so it's kind of like protecting or like like retroactively filling in the blanks that and one of the ways that Neil deGrasse Tyson was alluding to it was like that this is like a proof of like some type of simulation.
Yeah,
And
I
this
think
is
it's all cope.
yeah, and this is what I'm like getting at here is like it seems as though they start because of like wanting to strictly separate so much from like reality from God or God from reality and coming up with like an artificial take, they end up with these really like wacky fucking outcomes.
They're just self-projecting their expectations and then calling it like an explanation. It's not an explanation. It's just mental masturbation. But it's fine. I mean, we're learning things from it.
Oh yeah, here's like the video. I'm gonna watch yours, but this is the oh man. Let me see. He pops up supersymmetry.
So, you know what supersymmetry is?
No, I don't know.
Supersymmetry is anti-de Sitter space string theory.
Okay.
So, you know what I described to you before, where
Yeah.
watch Suskind's video. So, what goes on is you're able to add we're today, I mean this video's old. So like today, we can actually create 3D models of the way in which we could predict how quantum particles would behave
Oh shit! I watched
in a
this one.
supersymmetry environment, which is supersymmetry is an environment where where it's literally at the boundary of space.
Yeah.
That's not the real space that we live in. So that's why the way he phrases it is, yeah, when we look at the equations that come out of our string theory equations, when we analyze the results within our models that we're using computers to generate, and we're looking at the kind of mathematical equations that the simulation is coming up with, they resemble a certain computer math code. Well, no shit, because the whole point that makes a simulation possible is having a fucking boundary. It's a closed system. You need to watch the Leonard Susskind interview.
Yeah, I did. I clicked on it, and it was one I watched about a month ago, and I was like an hour and 25 minutes in. Was there a point like a timestamp you wanted me to watch in particular?
The first 30 minutes. If you want, let's watch together. 1 second, I'll be right back.
Yeah. Here.
All right, let me set up this fucking video.
Oh yeah, Beesma. I don't know if you saw this, but like besides the second Big Bang or whatever, they also came out with this thing.
We live in the wrong
Because I
country.
was also curious about what other copes they come up with, and they came up with this concept of dark dimensions in string theory to explain like that all of this dark matter shit is actually matter, regular matter, but it's held inside of a dark dimension, so we can't experience it in the lower dimensions.
To be
Alright, I'm starting it.
Yeah, I'm watching.
described by string theory. No physicist has ever
watching,
won a big
guys?
prize for string
Hey,
theory.
Kyle.
I can tell you with absolute certainty that it is not the real world that we live in.
No.
So
Kyle, repent or
When
perish.
Did you hear him?
Yeah, I can
All
hear
the
him.
results that they get from string theory, he says definitively he can state that it is not the real world.
Nigga theory.
to start over,
So we need to start over.
In a groundbreaking revelation, Leonard
You need to get
Susskind,
saved because you're
one
an
of the
unsaved
founding
Catholic. That's
fathers
what you
of
need to
string
do.
theory and professor of theoretical physics
Catholics
at
go to hell
Stanford University,
100% a
makes
hold
a
of them.
stunning
So
admission.
Kyle,
String
we're trying to
theory
watch something.
has failed, and many physicists don't know what to do.
they're scared. They might not get a job.
The theory that once promised to unify physics has instead generated 10 to the 500 different possible solutions, or vacuum states. Some theorists maintain that each mathematical solution corresponds to a physical reality, a legion of multiverses. However, the extensive
That's
efforts to
cool.
tame this so-called landscape through, for instance, KKLT vacuum stabilization mechanisms suggest an implicit acknowledgement that the multitude of universes is senseless. I'm Kurt Jaimungal, and on this channel, I explore unification in physics and philosophy using my background in mathematical physics from the University of Toronto. Today, it's a special treat since we have the legendary Leonard Susskind in rare, candid form, revealing his unconfined thoughts for the first time.
So we should certainly be on the lookout for ideas which are not the consensus. We should be watching for them and not immediately dismiss them.
We also talk about what it means that the universe is a hologram, why quantum entanglement is equivalent to wormholes, why supersymmetry is absent in our universe, why we lack a quantum description of
Do you see what I mean? Do you see exactly what he says?
Yeah.
Supersymmetry, it does not exist within our universe. It's a heuristic. You get what I'm saying?
Mhm.
That's why, in that video when they're having like a self-masturbatory talking session with fucking
Neil deGrasse Tyson.
Neil deGrasse Tyson, and he's up there. He's literally a fucking circus ringleader, like a crazy dude with an afro, talking about how they're finding computer programs within supersymmetry. Their supersymmetry simulations. That's what Neil deGrasse Tyson is trying to insinuate, that the world is a simulation. No, fucking supersymmetry is not the fucking real world. It's fucking stupid. And Leonard
Do
Susskind
you,
explains why.
consider space.
Sorry, go ahead.
I was just gonna say, like, do you think simulation theory is just creationism for atheists?
No, that's the wrong way to. That's not a genuine way to talk about it. You have to
Yeah,
talk
you're
about it
right.
with
You're
their
right.
own. Yeah, that's just stupid. That's just a gross overgeneralization. That's
Well,
to
it just
assume that
seems,
creationism
yeah.
is real. Creationism isn't real either in the way that you're trying to assume. Now, I know
Well,
what
it's
you're
like,
trying to say, which is like, you know how they accuse us of like being like creationists and all this, and they try to straw man our position. Is this like simulation theory like a straw man?
yeah, or like,
It's more
there's
accurate to
something.
say that no, simulation theory isn't plausible because supersymmetry doesn't exist in de Sitter space. That's
Okay.
that's just the best way to put. I mean, I wanted to get through the videos so you could hear it for
Yeah,
yourself.
yeah. Let's watch it.
Space, and why young physicists are afraid, even discouraged, to tackle these fundamental problems. Professor Leonard Susskind, welcome to the Theories of Everything podcast. It's been years since I've wanted to speak with you, and I'm glad to be able to get this opportunity.
Glad to be here.
What are you most excited about in physics today?
That's a very hard question. I'm excited about a different thing almost every day. Ask me an easier question.
Okay, how about today in particular? You said that you have some deadlines, so why don't you talk about what you're working on?
Well, I've been working on for some period of time, trying to understand the quantum mechanics of cosmological descriptions of the universe. Technically, it's called de Sitter space. And we live in a space-time that there's some evidence, more than some evidence, a lot of evidence that it's tending towards something called de Sitter space. What is de Sitter space? It's an exponentially expanding space, driven by what is called dark energy. And we don't understand the quantum mechanics of those kind of space times. So I've been thinking about that on and off, on and off for 30 years, but in a focused way for the last 5 years.
So, what are some of the problems with de Sitter space in string theory? Because it's primarily anti-de Sitter space.
That's correct. Anti-de Sitter, well, it begins with the so-called holographic principle that the world can be described by a theory that lives, so to speak, on the boundary of the space-time. That's the holographic principle.
So the holographic principle is
Yeah.
supersymmetry. When you have crazy Afro man computer simulation string theorist guy start talking about how what the results that he gets from their string theory applications within supersymmetry, within a holographic, in an environment where they're already presupposing the holographic principle, then yeah, they're gonna get fucking computer code back. It's stupid.
In this room, I'm sitting in a room now. The room is filled with stuff. The description.
So just to be clear, when Elon Musk is talking about, oh, I believe in simulation theory too, he's not a string theorist. He's just an engineer.
Yeah.
It's just
Of that stuff, ordinarily, the ordinary description of that stuff is that you have quantum fields in the room, you have particles in the room, you describe them in an ordinary way. In quantum gravity, we know now that the correct, precise description is in terms of a theory that lives on the walls of the room. And that's a little bit unusual, a little strange. It's called the holographic principle. It's widely accepted. While it was Tufte and myself who put it forward a long time ago, this is a widely accepted principle now, that there are enough degrees of freedom just on the boundary of the space to describe everything in that region of space. Anti-de Sitter space is a space that has a boundary, and that boundary is very, very important to the description. It's where this holographic description takes place. We don't live in anti-de Sitter space. Nothing like it. We live in something called de Sitter space. Now, you might get the feeling that de Sitter space and anti-de Sitter space are almost the exact opposite of each other. Yeah, more or less. That's correct. So we live in the wrong kind of world to be described by theories of anti-de Sitter space. We have to start over again. We have to start building theories that don't have boundaries, because de Sitter space does not have a boundary. Anti-de Sitter space does. We have to start over again, and there's not a lot of people thinking about it.
Now, if our universe is de Sitter, why is it that not
you know
plenty of
why
people
no
are
one's
thinking about it?
Wait, say it again.
Do you know why no one's thinking about it?
Because the institutions for like the last 60 years within the institutions and all of these academic departments have been pouring money into string theory, and they've been like criticizing and ostracizing anyone like that's been looking into anything else that is like apart from the masses.
Right, and that motivates current string theorists to keep trying to produce results that confirm their own bias. So basically, it's because guys like Neil deGrasse Tyson keep prostituting the science.
It's me. I don't know.
Well, one of the technical reasons in de Sitter spacetime, the boundary is time-like and at future infinity, and so holography is more difficult to formulate, whereas in anti-de Sitter spacetime, the boundary is space-like at spatial infinity.
In anti-de Sitter space, the boundary is the boundary of space. There is no boundary to space in de Sitter space. What you're probably thinking of is that there's a kind of boundary to time. But that's not the kind of boundary that the holographic principle envisions. So we need to start over. If you were an astronomer and you look out at the world, you would, the furthest distances possible, you would discover that there is a kind of boundary. It's the horizon of your space. The horizon is not the kind of boundary that anti-de Sitter space has. So you're asking me to explain some very technical things. But let me just say that the world we live in is not the kind of world that the mathematics that we understand, the mathematics of anti-de Sitter space is about. So we need to start over again where the boundary of space is a horizon, not a boundary in the same sense. But you're asking me questions which are, I think, just too hard for me to explain.
So would there be a DS CFT correspondence?
No.
Or only in extremely special cases?
No, in no case. In the sense of the usual holographic principle, where the boundary is a boundary of space, it most certainly is not a conformal field theory. CFT means conformal field theory, and that's exactly the wrong thing for de Sitter space. It's exactly the right thing for anti-de Sitter space. And we don't know what the right thing is for de Sitter space. So I've been experimenting around for a number of years with a simple model, trying to argue that it describes some kind of de Sitter space. I'm not sure my colleagues agree with me. But the bottom line is we know very, very little about it. So that raises a question that you asked. Why isn't everybody thinking about it? Beats me. I don't know. You'll have to ask them. When I ask young people, they say it's too hard. And I say, well, come on, it's virgin territory. Anything that you manage to say about it will be new. Thinking about old things is very hard because almost everything has been said by somebody in the past. This is open territory. Just get into it. And they say, no, they're scared. They're scared. They might not get a job. They might not be able to make any progress. It's too hard. Yeah, they might be right. Maybe they won't get a job, but it's not the criterion for whether you should work on something in science. You should work on it because you're curious. You should work on it because it's relevant to the real world. And not, in my view, be afraid of it because you might not get a job.
So
what if it's
speaking
just
of,
a coping
of
mechanism,
passion
Mr.
or
Susskind?
curiosity, string theory's been a passion of yours for
Think about it, right? Like
Yeah.
at the end of the day, it's almost like they're peddling a religion, right? Like it's something that he can't even find a way to convince young people because it's something that they're gonna have to take a leap of faith on. Isn't that crazy?
Yeah.
Anyways.
decades. How has your passion evolved?
Since 1969. How has my passion evolved? That's a psychological question, and I'm not a psychologist. Ask me a physics question.
How about this? How about I quote you from a podcast with Krauss? He said,
Okay.
describing string theory, look, string theory is supersymmetric. It fails when you don't make it supersymmetric. It has exactly a zero cosmological constant, has a slew of features that are different from the real world, and that you can tell Krauss with absolute certainty that string theory with a capital S is not the theory of what you'd call the real world. And I think you said, I can tell you this with 100% certainty. You being Krauss.
There's a precise, very precise mathematical structure called string theory. It's so precise mathematically that mathematicians have won Fields medals for contributions to it. Field medals. It's a very, very precise mathematical structure. It exists. It's well defined.
Doesn't
But it
exist.
has some features which the real world doesn't. As you said, supersymmetry, whatever supersymmetry is, special mathematical features that make it solvable and make it possible to calculate things in it. And we know for certain that the world that we live in does not have those special features. I call the very precise theory string theory with a capital S. Now, can string theory be expanded into new territory, which is not so very supersymmetric? We don't know. We don't have a generalization of string theory, which is not supersymmetric. People talk about it all the time. They talk about breaking supersymmetry, blah, blah, blah. But there is no real theory of that. Maybe it exists. Maybe there exists a slightly expanded version of string theory, which is a little more general, which is not supersymmetric. But we don't have that. So I can tell you with certain string theory with a capital S, the precise mathematical structure, which, as I said, mathematicians win prizes for. No, incidentally, no physicist has ever won a big prize for string theory. I can tell you with absolute certainty that it is not the real world that we live in. So, so what do we make out of that? I don't know. We need to expand the theory. We need to generalize it a little bit. And in fact, I can say a little more, that no known version of it, no precise known version of it exists in de Sitter space. We live in de Sitter space. So we have a lot of work to do. And it takes not only great brilliance and great smartness and so forth, it takes some courage to move into areas which are so unknown that who knows, we might spend decades trying to unravel it. But that's where we have to go. I wish I could tell you, I see the way, look, I'm 84 years old. I'm not the one who's going to do this. It's going to be young people who will do it. And at the moment, I actually don't know any young people who are working on this.
Who are working on a generalization of string theory?
Yeah, a generalization of string theory, which is not dependent on these very special features, usually called supersymmetry, but they're just very special mathematical features that make the theory simple and easy to solve. Again, we don't live in that world, and I actually don't know anybody who is working, striving to try to expand the theory into either de Sitter space, which is not supersymmetric, or just more generally into an expanded version of the theory. And older people worked on it in the past. They worked on something called spontaneous breaking of supersymmetry. Don't worry about what it means. It just means the theory wouldn't be supersymmetric. And they failed. Now, that's not a criticism of them. I worked on it and I failed. That's not a criticism of anybody. But it's a fact that there is no precise theory which is not supersymmetric. That is intolerable in a sense. It can't stay that way. We have to describe our world. That's our purpose. And as I said, I don't know anybody who's actually working on that. If you were to send out a message to all the world's theoretical physicists, is anybody working on a generalization of string theory, you probably find some yeses, probably mostly among older people. And somehow we have to change this.
The difficulty here comes from the elusive question of what defines
there?
string theory.
Yeah, I'm watching.
This question
There's
was
the
infamously posed by researchers at String 2023, and there was no uniform answer. Susskind's response frames string theory as any theory of quantum gravity. However, critics argue that quantum gravity is just one single approach to a theory that combines quantum mechanics with gravity. Furthermore, string theory is merely an example of a quantum gravity theory, not
That's
the
true.
example. There's loop quantum
It's an
gravity,
example.
there's causal sets, for instance.
Yeah.
At what point does redefining a theory by changing the capitalization from big S to little s become an example of wanting to have one's cake and eat it too? In other words, to claim success despite what even people in the field themselves call a failure. For more on this, see the talk by Edward Frankel. Critics liken this to if string theory as a field said, hey, my flying car prototype didn't work, but I'm not a flying car manufacturer with a capital F. I'm a successful flying car manufacturer with a lowercase f, because success to me now means any movement from point A to B, where bumps on the road momentarily lift you. And I can achieve that even by calling you an Uber. Oh, and by the way, I've changed my definitions while along the way systematically destroying the careers of anyone working on actual flying vehicles.
And somehow we have to change this.
Now, this is huge news, at least to myself,
Yes, it is.
because you're one of the founders of string theory.
Yeah.
And string theory is one of the, if not the most dominant by far, actually,
By
in
far.
theoretical physics,
Yeah.
for fundamental physics. And for one of the founders, the fathers, to come out.
Before you go ahead, before you go ahead, let me tell you what the good news about string theory is. It's a mathematical theory which contains both general relativity and quantum mechanics. In that sense, it's an existence proof that quantum mechanics and gravity can coexist with each other. For many years, people thought that quantum mechanics and gravity were at each other's throats. They couldn't be reconciled. We know, on the basis of string theory in particular, let's call it anti-de Sitter space string theory, we know with certainty now that quantum mechanics and gravity can coexist. Capital S string theory combines the two in a very beautiful way. We know, for example, with certainty, because of this supersymmetric theory, that black holes respect quantum mechanics. It was thought by Hawking for many years that quantum mechanics and black holes couldn't be reconciled, standard principles of quantum mechanics. We know that's false, and in that sense, we have an existence proof for the consistency of quantum mechanics and gravity. That's no small thing. That's a big thing. And that's mainly what string theory up till now has done for us. Apart from there's another thing that's done for us. In another form, string theory has described hadron physics. Hadron physics means protons, neutrons, and mesons, but it's a separate issue. String theory is a very fundamental theory, has done this one spectacular thing. It's given us an existence theorem that quantum mechanics and gravity can exist together. And as I said, that's no small thing. It's a major development in physics over the last 20, 25 years, maybe more. And so string theory in that sense is not a failure, but by no means is it a failure. It's a spectacular achievement. But it does not yet describe the real world. It has to be expanded, it has to be generalized. And we don't know how.
What other approaches exist that reconcile general relativity with the standard model?
Well, the standard model. Sorry, this is not the question of reconciling general relativity with the standard model. You mean the standard model of particle physics or
Lambda
cosmology?
CDM.
Particle physics.
There is none. There are none. There simply are none. If there was one, we'd be working on it. That's the problem. String theory in some way looks a little bit like the standard model. It has fermions, particles, like electric.
So basically what
Yeah.
this means, right? Lambda CDM, right? Basically what he's denying is that string theory was never assuming the same premise of lambda CDM, which is that there is cold dark matter energy. You get what I mean?
Wait, say that again. So string theory does not take into consideration that like when it was founded, like it wasn't
He's
taken into
literally saying
consideration.
once and for all right now in this video, these two quote unquote theories have nothing to do with each other.
Okay, okay.
But a lot of science bros would have you believe that string theory and its conclusions about black holes are somehow related to whether or not dark matter and dark energy exist. You get what I mean? It's
Yeah.
cope.
Can have with the appropriate version of it. It can have electrons, it can have photons, maybe it can even have quarks, but always this supersymmetry gets in the way of comparing it with the real world. So in many ways, it does look like the real world, some versions of it, but in many ways, it doesn't look like the real world. So we'd like to find something that has the good features without the bad features. Still a work in progress. We can't do that yet. And is there anything else? Not to my knowledge. Not to my knowledge.
What about Latham Boyle and Garrett Lisi, or Peter White, or Eric Weinstein, or Julian Barbour, or Stephen Wolfram? They all have their own theories of everything.
Okay, I will ask you, what do you think of them?
Well, I can tell you what each of their theories are.
No, we don't have the time for that, obviously. I would love to know, but I know that Stephen Wolfram is a great advocate of little checkerboards. What do we call them?
Cellular automata, at least before, and now it's been generalized from graphs to hypergraphs.
Okay. That certainly doesn't contain either gravity or quantum mechanics. So it's a failure.
Well, Eric Weinstein's is
He's
that
just shitting on somebody
general
else's
relativity
project.
itself contains the ingredients of Petit Salam,
What do you think?
along
Do you
with
think
the
like,
3 generations.
even though he wants to, he is like saying like that we have to start over, we have to look at other theories. He still has like this like
He
it's
has
almost,
faith in his own pet project. Yeah, of course.
yeah, like it's been like so deeply rooted, like this way of thinking, this
Yeah.
like this
I think he's
habit.
got some points, right? Which, I mean, they're
Mm,
rational considerations here, which is, it says, it's able to account for black holes. Within its own model, it was able to provide an evidentiary proof, or excuse me, an existence proof for black holes. Okay. That it was possible that within string theory, it is possible to have black holes in string theory. And then mathematically speaking, quote unquote mathematicians who have worked on the formula have won commendations or awards for validating the mathematical theory itself. The proof itself is a valid proof.
yeah,
It's just it's not able to replicate anything in de Sitter space. Anything outside of supersymmetry, it's unable to unable to predict anything. I don't know really what that means because I'm not a mathematician. I don't know what the other what other theories are. And that's kind of what Kurt Jaimungal is asking him now. How
yeah.
does yours fits with them?
The question was basically like if he was shitting on
Oh,
the
yeah.
cellular automata like right off the rip, just because um he's had like I don't know how many
Oh,
decades
yeah, that's
of
right.
like, yeah,
No, no, no.
like,
It's because he says it doesn't include gravity and it doesn't include quantum mechanics. So that for him, he doesn't see that as addressing the problems as he see it currently. So, okay, grand unified theory is trying to resolve Einsteinian relativity with quantum mechanics. So if you have a quote unquote theory of everything that's trying to be a generalized theory for all fundamental physics, then in Suskind's mind, it would have to address those two, right? At least.
yeah.
But because this checkerboard theory of everything doesn't, he's just dismissing it.
Okay, okay.
And cosmological constant, which I could explain to you at another
I
point.
don't know who Eric
I
Weinstein
yeah,
is. I don't know.
I don't think it's just a matter of, oh, he's so invested into string theory and that's why. That's not fair. I don't think that's fair.
Theory, so
So
I
there
can't.
is something there to string
Do you know
theory. It's
Julian
just,
Barbour,
yeah, we
or
just
Latham
his
Boyle?
argument is that we just don't know
Julian
what it is yet.
Barber is the fellow who doesn't believe in time.
Yes, that's correct. That's correct. Yeah.
I believe in time. So, I think what he says is trivial. That the whole world, what does he call it? The block universe?
I believe it's shape dynamics.
No, then
Oh,
I
yes,
don't know. I don't know.
Okay, here's something else you said that was super interesting. SU5 may at some level be correct. And I believe you said, you then corrected yourself and said, well, or something that has SU5 as a subgroup.
Yeah.
So can you explain why you believe at some level that's correct? Because many people hear that who are physicists, many people who are, and you can be technical, just so you know, and they hear that they think, oh, grand unified theory, that's been disproven, proton decay. So
No,
in
no,
your mind, when you hear
I don't think
SU5,
it's
what are
a
you thinking
reasonable
of?
attitude. When Glasgow and George I put forward the SU5 theory, there was a spectacular way in which the ordinary particles, electrons, quarks, all the ordinary particles fit into SU5 multiplets. And it seems to me that's no accident. The way that the neutrinos, electron, protons, the standard model fit into the SU5 in a very nice way, I feel is not an accident. Maybe it is an accident, but I feel it's not an accident. Now, their original SU5 theory was too simple, for sure. It was certainly too simple. People have generalized it, 010, 016, all kinds of things, but all of those things contain SU5. And the particles fit into the SU5 multiplets the way that in these other more extended theories, the particles still fit into the SU5 group in pretty much the way that Glasgow and George I said. So I feel it's not an accident. I could be wrong. But the statement that baryon decay doesn't happen, I think that's premature. It's always kind of the case that people try to make their theories so that in the very next experiment, whatever it is they're looking for,
Right.
always, not always, many times, people will tailor their theories so that the next round of experiments will discover what they're looking for. That was true of supersymmetry. We know that supersymmetry is not a...
Do you see what he said right here? So
Yeah.
he doesn't believe that string theory, right, itself is arbitrarily manufacturing to try to get the results that it's looking for, but he does admit that supersymmetry does. Do you remember what I said earlier, near and far? Where you sent me the first video with Neil deGrasse Tyson and with the
Oh
crazy
yeah,
guy
yeah,
running
yeah,
computer
yeah.
simulations, and I was like, no shit. If it's within supersymmetry, of course you're gonna get a bunch of codes that pop back out, right? And look what he's
Yeah.
saying here, right?
Not always, many times, people will tailor their theories so that the next round of experiments will discover what they're looking for. That was true of supersymmetry. We know that supersymmetry is not an exact symmetry of the world. So for years, people made these theories in which an approximate supersymmetry...
You still watching?
Yeah, I'm still watching. Yeah, play that one.
March 7th. Well, partly it's taken to these very strange images that are behind your head right now. These are pictures of equations. I've been, for the last 15 years, trying to answer the kinds of questions that my colleagues have been raising. And what I've come to understand is that there are these incredible pictures that contain all the information of a set of equations that are related to string theory. And it's even more bizarre than that, because when you then try to understand these pictures, you find out that buried in them are computer codes just like the type that you find in a browser when you go surf the web. And so I'm left with the puzzle of trying to figure out whether I live in the matrix or not.
Wait, you're blowing my mind at this moment. So you're saying, are you saying your attempt to understand the fundamental operations of nature leads you to a set of equations that are indistinguishable from the equations that drive search engines and browsers on our computers?
That is correct. So
Wait, I have to just be silent for a minute here. So you're saying as you dig deeper, you find computer code writ in the fabric of the cosmos.
Into the equations that we want to use to describe the cosmos, yes.
Computer code.
Computer code, strings of bits of ones and zeros.
It's not just sort of resembles computer code, you're saying it is computer code.
It's not even just is computer code, it's a special kind of computer code that was invented by a scientist named Claude Shannon in the 1940s. That's what we find very, very deeply inside the equations that occur in string theory and in general in systems that we can say are supersymmetric.
Okay.
Time to go home, I think. Where are we going to go after? So are you saying we're all just, there's some entity that programs?
They dictate that there are certain things that are actually strings of ones and zeros. That's just digital data, but it's not just random ones and zeros. As I mentioned earlier, let me talk about something that you probably do every day, but I don't know if you're a computer scientist or not. Most of us sit at our...
Sounds that kind of fluency, I said.
Okay, well, most of us sit at our computer screens and we type on the keyboards, and we then send these, if we're using a browser, we're sending strings of ones and zeros elsewhere. But on the other hand, in the transmission process, there's always some fluctuations. So a zero that you type here because of static in line might be read as a one at the other end and vice versa. And so in fact, when you sit and type on the keyboard, your computer's doing something behind your back. Namely, it throws in a bunch of extra ones and zeros, and these things are called error correcting codes, so that the computer at the other end can look at the whole collection of what you typed plus what was sent and figure out if there were bits that were being flipped back and forth. And that's how you get accurate transmission of digital data. Among the codes that are used for this purpose are a special class of codes that are called block linear self-dual error correcting codes. They were first, in fact, the Shannon extended checksum code is an example of one of these things. These are the codes that we find buried in the equations. Not just any code, but these self-dual error correcting block codes. It's quite remarkable for anyone that I've talked to. We have no idea what these things are doing there.
Any literature out?
I'm sorry?
I got to ask you something. Your discoveries of these sort of error correcting code within the laws of physics themselves at the depths that you're researching them what I wonder is we live in
Do you notice how much more bling he's got?
Yeah, look at him, dude.
the
After he
age
got all
of
this fucking
information
funding, man. I'm
technology, so
sorry.
we all have
Yeah,
a certain
look at 'em.
fluency. So it's in our brains to think that way at some level. Could it be that you know how the saying goes, if you're a hammer, then all your problems look like nails, and you solve them by hitting them. If now we are in an IT revolution, and you're finding IT solutions to your problems, maybe it's just the fad of the moment, and you're forcing a solution that is either not real or there's a better one awaiting in a revolution that has yet to occur.
Sure. So the last time I was here, I actually misspoke. I used the name of Shannon when I meant Hamming code instead. So first, let me correct that for this wonderful audience.
Error correction in action.
That's right. Error correction in action. Absolutely. But in our work, it's first of all, we don't know that it's the physics of our universe. There is a large experiment underway that Lisa knows a lot about in Geneva because she has written papers about possible outcomes in these observations.
Lisa, are you flying to Geneva tomorrow?
I am, but not for that.
Not for that, okay.
So the Large Hadron Collider is going to explore more of the structure of our universe. So first, the mathematics that I have done will only become physics or relevant to nature when the LHC or some other observational device says the idea of supersymmetry is correct. Then it will kick in. So that's a big if. There are lots of physicists who don't believe the universe will be supersymmetric, in which case all I've done is an interesting mathematical fairy tale.
So supersymmetric proposal.
Interesting mathematical fairy tale. Huh.
What do you think about that?
So, I mean, like literally what he said. If it turns out that our world is not supersymmetric, then what he's been doing is nothing more than an interesting mathematical fairy tale. This whole holographic universe shit is based on a mathematical fairy tale. And that's why I was
Fucking
like,
Cope.
Yeah, it's literally coping pill. And then Susskind is like, that's not the really fucking universe.
Yeah, like all
So
of this
it would be
stuff is describing an anti-de Sitter space reality.
Right.
However, we don't like the us humans in the real world on Earth and shit. We are not living in an anti-de Sitter space. We're living in a
De Sitter space.
yeah, in a regular de Sitter space. So it's like these like there is no rubber meeting the road, so to speak.
There's no supersymmetry.
And then there's like I don't know if you saw like that new magazine on the right side, but it's like the physicists are searching for like the dark matter inside of these dark dimensions.
Well,
It's like
you have like idiots who are still like, oh, they're inside of stars now. That's why we haven't found them, everybody. The dark matter is inside of the stars. That's why we're not finding it in open space. Because here's the thing, that's almost kind of like an unfalsifiable claim. I'm saying almost like, because if it's physical and it's observable, theoretically, hypothetically, we could measure it, but as far as we know right now, there actually isn't a way for us to get inside of a fucking sun. You know what I mean? We don't know. One of the mysteries about stars in general is we don't know exactly what the composition of it is. You have people
No,
coming out of the
to an
woodwork
extent. I
now.
mean,
wait, flip do.
Go ahead.
Oh,
I
I
was just
was
saying to an
gonna
extent. To an extent, we do know the composition of like. Do you mean like what it's made up of?
Yeah.
Yeah, yeah. I mean, to an extent. I mean, like we know what the sun is made up of. I wouldn't say every star like
No,
that we
we actually
see.
don't.
Oh, we don't. I thought we
No.
did. Like the
Look it up.
gases that it's made of.
When you look at like the Earth, that's another mystery. Like we actually don't know what the composition ratio is even within the planets. There's no way for us to deduce this unless we actually drill down to the center of the Earth, so to speak.
Yeah.
But based on other observations and measurements, magnetic shift and all of this, we can assume that, oh, well, only certain elements within the periodic table, like iron, is going to be able to account for the magnetic shift that we observe on the surface. It's probably composed of like a hard metal within like this sector of the periodic table. We've deduced that it's most probably iron. We don't know how much
Yeah.
iron. So when it comes to like stars, we actually don't know what it's made out of. But what we do observe is like the radiation from the sun. And that's the thing is,
You mean we're
yeah.
jumping to conclusions? Like we're
I'm not
we're
saying we're
making
jumping.
logical conclusions in
we're
it to an
we're
extent. Like
deducing and
yeah,
using rules of inference, right? But
yeah,
what I'm trying to get at is like, okay, so we have these people coming out of the woodwork now that are trying to revise, and they're hypothesizing, oh no, the dark matter actually exists within the stars themselves. So that's why we haven't been able to observe it, obviously. And if that were true, then it would account for, the extra mass as a part of the galaxies. For right now, it's kind of like an unfalsifiable
yeah,
theory. But
yeah.
anyways,
discovered at the very, very next accelerator experiment with no good reason. No good reason. It's just they wanted it to be true. They wanted to discover it. I think the same is largely true with proton decay. That
I don't know.
that
Maybe there's an angel
in
sitting at the
fact,
center of the star.
let's put it this way: over the last, how long has it been that
I mean, I
proton
still
decay
think it's all
ideas have been
interesting.
around for
Yeah.
almost 50 years?
I mean, I find it
Something
funny
like
because
that.
it's like reading a mythological book sometimes when
Experimentally,
looking at science papers,
the
and you're like,
upper bound on
oh, what?
the lower bound on the
Mhm.
lifetime of the proton
Like
has gone from
everything we
about
see is
10 to the minus
illusory.
30, 10 to the
Like what?
32 years to
What's going
all
on?
of 10 to the 34 years, or 10
what's
to the
what's that one
33 and a
show
half
called? It's like
years.
Black Mirrors.
There
It's sort of
hasn't,
like that. It's like an episode. It's like Black Mirrors because like every single scientist they have like their own theoretical line that they're going through, and they assume certain principles and certain conclusions in order to get to where they are. So like for example, like the physicists who would say everything that we see is illusory, and I mean issue. I mean, how does he know it's illusory? I mean, if it's all illusory. And so it's kind of like that. It's because you don't have that grounding that they're coming to certain I guess, logical conclusions to an extent. They're deducing these things, but uh, they're taking their uncertainty and going, well, everything's illusory then.
Could be.
You
I
didn't
mean,
play it.
I respect the fact that Susskind is, like he is giving, like like I don't think he's like a kook at all. Like he's being pretty reasonable about what string theory, like he's representing his theory well, and he's owning up to it. So
I thought string theory was disputed already.
yeah,
Like,
we're literally that's what we're watching right now.
Oh, okay.
Alright, I'm gonna
Yeah, because it came about by I mean, oddly credible person, oddly credible. And I say that because it's like, I don't know. I mean, I feel like the guy, I don't think he really had much to the back of his. It's kind of weird. It's like his theory was just kind of wholesale accepted based on who he was,
Yeah,
and then
because okay, so like we're literally watching it
it
right
just doesn't
now,
align with
right?
reality.
No, the reason why is because it does provide an existence proof for black holes, which is within its proof model, you can have black holes. It can predict for black holes. Um, or and the other thing is and these are his 2 points. His second point is that mathematicians have validated the proof theorem itself and won medals because of it. So it's not just like bunk or junk formulas.
Yeah.
So, and it is one of the theories at the time that they had that was trying to account for both gravity and quantum mechanics. And that's
Yeah.
why it was looked at as the holy grail of, if we could have a grand unified theory of something, this kind of has the best shot at it based on other plausible theories that we might have had at the time.
Wait, could it actually predict black holes? Like that actually happened, or it
Yeah.
theoretically
So
predicts black holes?
so black holes do exist within its system. Like
Yeah.
it provides a valid proof for black holes. And I believe we have observations of them too. Again, these are deductive observations because you can't, there's no light, right, from a black hole, but we can see the way that
Yeah.
it bends light around it.
Yeah.
I think JWST also confirmed it. I'm not sure. I have to look at the stuff again.
Yeah.
But anyways, all right, I'm starting it again.
They're looking for. That was true of supersymmetry. We know that supersymmetry is not an exact symmetry of the world. So for years, people made these theories in which an approximate supersymmetry would be discovered at the very, very next accelerator experiment with no good reason. No good reason. It's just they wanted it to be true. They wanted to discover it. I think the same is largely true with proton decay. In fact, let's put it this way: over the last, how long has it been that proton decay ideas have been around? For almost 50 years, something like that. Experimentally, the upper bound on the lower bound on the lifetime of the proton has gone from about 10 to the minus 30, 10 to the 32 years to all of 10 to the 34 years, or 10 to the 33 and a half years. There hasn't been a huge change in the constraints.
You know what's funny? Protestants, dude, they don't like this shit.
Wait, why? What happened?
Because they're I mean, dude, he didn't want to stay and watch. So funny, dude. Protestants are so
Yeah,
funny. Anyways.
yeah, Protestants are something else.
From the time of the early George I. Glashow
Hey,
theory.
I'm a Protestant.
So I think it's quite premature.
Are you
If the
really?
proton decay occurred at 10 to the 35,
Technically,
a lifetime of 10 to the 35 years,
You're not a Protestant?
10 to the 35 seconds.
Protestant?
Years? Whatever.
We're
wouldn't know.
Catholic. We have a blood feud.
We wouldn't know. So I think there's plenty
You're
of room in these
Catholic?
theories
I
for
thought
the
you were
proton to be stable at the current experimental
a
limits
Protestant.
and still be unstable the way SU5 needs it to be. But I'm guessing, I think people have just given up on that subject because they don't see ways of experimentally confirming it
Yeah, no
other than
shit.
just wait.
And everybody's waiting.
You know, the proton decay is an interesting thing. The lifetime of a proton is known to be longer than about 10 to the
So I have a
33
question.
years, I guess. Okay. That's how then can you ever detect a proton to decay?
Okay.
You take a
I
proton
guess
and you
I'll wait
sit there
until you
and watch
finish.
it for 10 to the 32 years, 33 years? No. What you do instead is you take 10 to the 32 protons, 33 protons, and you wait for one to decay out of all the huge number. It's an incredible thing that experiment can be done. Just think about it for a minute. How many protons is 10 to the 30? A huge number. And you sit there waiting for one to decay. And it's kind of a spectacular thing that's really at the edge of technology. And if the proton was a little more stable than that, instead of 10 to the 33 years, it was 10 to the 35 years, we would have no chance of discovering it for another, 50 years. So I think it's premature to say that proton decay has ruled out SU5. I think that's premature. But, it really doesn't matter what I think. We just have to sit and wait.
Can you talk about the landscape?
Yeah, again, string theory is a peculiar theory in which the behavior of space-time and so forth is not an input. It's an output of some equations, and those equations have many, many solutions.
Do you get this?
Yeah.
String theory is a peculiar theory in which the behavior of space-time and so forth is not an input. It's an output of some equations, and those equations have many, many solutions.
Do you get that?
The meaning of that is that there are many possibilities within string theory for the coupling constants, for the masses, even for the particle spectrum itself, for the cosmological constant, for all the parameters of the theory. It's not a single theory of the universe in which the parameters all are necessarily fixed by the equations. Not at all. Instead, it's a theory that has many, many solutions to its equations, and those solutions, each one of which has a particle spectrum, it has a collection of coupling constants, and so forth.
Quantum computing
Again,
would be really interesting.
I'm speaking about the precise version of the theory, string theory with a capital S. If we ever learn a theory which is an expanded version, it's very likely that expanded version will have even more possibilities. How many possibilities? People always quote 10 to the 500 different possibilities. It's much more than that.
That's insane.
And looking for the right version of the theory is very much looking for a needle in the haystack. That collection of theories, that collection of solutions of the theory is called the landscape. It's called the landscape by me, and it's just the collection of all possible solutions of string theory, of the equations, all the possible values of coupling constants, all the possible values of the cosmological constant. And it's a huge, huge number, huge landscape. How we find a way around in it, even if we ignored the question of supersymmetry, even if we ignored that particular issue, is just too many to sort through. What we do about it, I don't know. We've really reached some very, very difficult things in the physics of fundamental interactions and so forth. Experiments have gotten progressively harder. If you go back to the early parts of the 20th century, how long did it take to do a quantum mechanics experiment? a year, something like that, maybe even faster. Now an experiment can easily take a whole scientific lifetime. You have to build a bigger accelerator, you have to build bigger detectors, you have to get the money to do it, and so forth and so on. So experiments from the beginning to the end can be 40 years or more, entire scientific lifetimes. And so we've run into the problem of the difficulty of experiment. We've also come, if this picture of string theory that has this wildly proliferating landscape of possibilities, if that's correct, then we've run into the obstacle of just too many things to sort. So things are hard. For that reason, many of my colleagues, myself included, said, let's put that on the back burner. Let's simply focus on the consistency of quantum mechanics and gravity. We know gravity exists. There's no question about that. And we have to be able to put it into our quantum theories. We have to be able to make it mesh with our quantum theories. And so most of the work that people like myself, people that I interact with on a daily basis, is about the connection between quantum mechanics and gravity. And theoretical constructions, theoretical models that contain both gravity and quantum mechanics. If they contain gravity, they will contain black holes. Hopefully, we'll be able to answer some of the paradoxes about black holes. But obviously, that's not completely satisfactory. We do want to have a theory which describes the real world of electrons, photons, protons, neutrons, and we're far from it. I think we're very far from it.
So, is there a reason to believe that with any of the possible solutions to the string theory landscape that there should be an associated universe to it? So I'll give you an example.
Yeah.
With Einstein's equations, there are a variety of solutions. You can even have a neutron star with a hollow center, technically. It's not like we think there must be a universe that corresponds to every solution of Einstein's equations.
If the universe is big enough, maybe so. Maybe if the universe is really big enough, then no matter how unlikely something is, it will occur somewheres.
How convenient.
If the probability of something is 10 to the minus
this kind of makes
100,
me. This reminds me of like
universe is-
the ontological argument, right?
Yeah.
Where it's like, or like
If you
that
can imagine
version
that
of
the idea is the biggest idea in your head, then of course it's going to be true.
yeah, yeah. That shit's, it's crazy to imagine like that they would like that there's almost like a parallel between like these apologetical argument for the existence of God and like these like weird cope things that they're using, like, oh well, maybe like this set of equations out of string theory describes like another universe, or the multiverse is true, so like that's why there's like 10 to the 500 possible,
Right, but in
so
this case, what he's assuming is that, and
yeah,
that's what I was going to say, his presupposition is that, yeah, if the universe was infinite, then anything would be possible.
yeah,
What we know, though, or is that we don't know, the most plausible deduction that we have based on cosmic redshift and what led this whole fucking cosmological revolution to begin with in the first place ever since Einstein and Hubble was that it has to have a universe. That's the most plausible hypothesis.
yeah,
So if it has a beginning, that means that it's not infinite.
yeah.
Sorry, go ahead. Yeah, go ahead.
No, that was basically it. It's just
Right. It's just in the God hypothesis of Anselm, we're saying that if it is the greatest in the mind, then it exists in reality. What he's saying
yeah,
is if reality is the
big
greatest
enough.
thing, right, then it's plausible that it's also real in our mind.
Yeah,
That's the inversion.
That's so weird. You're talking about being atheist versus being a theist. Or you're talking
Yeah.
about string
Yep.
theory and all this
No,
shit.
no, no, no. Being an atheist versus being a theist. That's what it really comes down to.
I think being an atheist, man. I think like even before I
Okay.
started getting back into Christianity, um, like I don't remember the exact chain of thought I was having, but it became very apparent on a mushroom trip that even if I were to kill myself hypothetically, that like my consciousness or like this sense of experience in qualia, that it's not like a one trick pony that only Nier is experiencing at this one time. Like that it would be continued to experience that basically that you're stuck in reality in some form, whether it's a reincarnation principle or whether there's an afterlife. Like there's no getting out of it. There's no, it goes to a void nothingness, like the atheist position, like that there is like some aspect to reality that is beyond our current like epistemological understanding. Um, and it is sort of like a cope, like a blind faith cope to just say like, well, we don't know, you know, like our epistemological ceiling, you know, like within like below that, like it doesn't describe this possible thing. So let's just assume that it, you know, like that's not the case, that the actual reality, like no, it's retarded. Like it's just very well, like it could be slightly beyond the ceiling, and we just don't have access to like that truth. But it's very much real, you know. So like that's it basically made it very apparent that there's something weird and fucky with reality that that it is not like just go all to black. Um and I didn't even, and at the time I didn't even want it. You know, I actually found it to be more comforting if it were to just go to a nothingness, like a true philosophical nothingness of no existence. But yeah, it just seemed like a very faulty ground to assume that would be that way. It seems to be more of a faith, um, or like some type of naiveness associated with like that type of perspective. That it seems a little bit more obvious that whatever this is, that it's going to happen again in some form, either again like through a different lifetime, or whether it's like there's a metaphysical ecosystem where you're continuing to exist forever, or whatever the case is. But like it is not a one-time thing. That's something that just became apparent to me.
Big enough to have 10 to the 200 regions of space, then you have more than enough to somewheres find your hollow neutron star.
You understand the point that just because
I don't.
there's the laws of physics that allow for something, it doesn't necessarily mean that
Yeah.
that the existence has to follow that possibility.
That's precisely what you're saying. You know what I mean?
Yeah.
I qualify my statement. If the universe is big enough, if it's big enough and it has, if its equations, first of all, a question, do its equations allow variety to exist? Do the equations allow a region over here and a region over here to be different from each other? Which the equations of cosmology,
Sounds like
inflation, eternal inflation do allow that the universe can have patches with different behaviors. And if the universe is big enough, then just on ordinary probability grounds, some place will have whatever it is you're looking for.
This is a cope, man.
Now, you're not used to thinking of
That's
things
so
which are
weird,
that
yeah.
big. So big that essentially anything can happen somewhere. You're not used to that. But that's what it would take to make this landscape theory and all that kind of stuff make sense. The universe just has to be very big. To our knowledge, the universe is exponentially expanding. It may have been exponentially expanding way, way into the past. If it was exponentially expanding deep into the past, it will be exponentially big. And what is exponentially big? It means very, very much bigger than the region we can see. We're used to thinking of the universe as being about 20 billion light years big. But that's just the part we can see. That's the part that we can see without running into a horizon. If the universe is old enough and exponentially expanded for a long enough time in the past, it could be vastly, vastly bigger than that.
Well, what I mean is that Einstein's field equations allow for the Schwarzschild solution, for instance, so static black hole. That static black hole is eternal, it's isolated, it doesn't decay, it doesn't even form. It's always been there and it will always be there. So that can't be a solution of the universe no matter how large the universe is spatially. In other words, GR is about the whole universe itself, and that any particular
That's
solution,
correct.
sure, you could say it's true in an isolated case, but if you take a solution seriously, it's about all of space-time.
Yes, Einstein's equations by themselves would say that a black hole will just sit there forever and ever in otherwise empty space. Hawking told us no, that's Einstein's equations are wrong about that. The black hole will evaporate. But I'm not sure that's relevant to our discussion here. Einstein's equations predict that a black hole is eternal. Quantum mechanics predicts that a black hole will evaporate. Which one is right? Almost everybody I know thinks that the quantum mechanics answer is right, but that's beside the point. We're not talking about black holes here. We're talking about what a physicist would call vacuum solutions.
Mm-hmm.
Vacuum solutions mean essentially empty space. When I say there's lots of solutions, I don't mean that the solutions describing black holes. I mean that are solutions describing empty space. And what are those solutions about? They're not about the presence of black holes. They're about the values of the coupling constants, about the values of the masses, about the spectrum of elementary particles. So each solution has a different collection of elementary particles. Some may have electrons which are 2,000 times lighter than the proton. Somewhere else in the space of solutions, you might have electrons which are 2,000 times heavier than the proton and neutron. That doesn't describe our world, but nevertheless, there may be many, many solutions like that. Some of the solutions may have large cosmological constants and not coexist with what we know. And some small fraction of them may have very, very small cosmological constants. We're not talking about the presence of black holes. We're talking about what empty space is like, what the rules of quantum field theory will look like. And as I said, there's a huge variety of those things. Now, your question is a good one now. Do we have any reason to believe that these different solutions will materialize and manifest themselves in our large universe? Is the universe big enough so that statistically all of these different properties will exist someplace in some region of space? Inflation is a theory which tells us that the universe is maybe exponentially and maybe even exponential, maybe even exponential times bigger than the region we can see. So we have no idea what's out there beyond the region we can see. It could be a bit of this, someplace, that, someplace else. And that's what the equations tell us. The equations tell us that if you wait long enough and the universe gets sufficiently big, it will be filled like a patchwork quilt with regions of different properties, some with small cosmological constant, some with big cosmological constant. And, there's just be a lot of stuff out there.
So about inflation, Penrose and Steinhard, they believe that inflation doesn't solve the fine-tuning problem. So Penrose, I believe, says that it just pushes the problem back about extremely specific initial conditions. What arguments against inflation do you find to be the most credible, or the ones that are the most challenging to you?
No, I don't. I think it's still possible that inflation could be wrong. but there's so much good confirmation, observational confirmation for it, that it seems to me very unlikely that it's wrong. Look, there are still people who believe in the flat Earth, for God's sakes. There's people who believe all kinds of weird stuff. Don't think about individuals. Think about the consensus of the largest fraction of physicists working on these things, and you'll probably be right. You'll probably, the overall consensus of the field tends to be right. The peculiar individuals, no matter how famous they are, no matter how brilliant they are, if they're off that consensus, and they've been off that consensus for a long time, they're probably wrong. That doesn't mean for sure that they're wrong. But don't look for the weirdos. Look for what the consensus of, the majority of well-respected, highly accomplished physicists believe. And you'll probably be right. They'll probably be right. There's no guarantee of it. There are very few cases where the consensus has gone wrong for a long period of time, just where some offbeat idea of some particular individual suddenly changes everything. I'm not saying it doesn't happen, but rarely. So Penrose, what can I say? He believes all kinds of things that I don't, that I wouldn't subscribe to. But more than that, things that the consensus wouldn't subscribe to. Steinhardt, I don't know what drives him. He seems to have a problem with inflation. I don't know why. Go to the observational cosmologists who actually measure these things. I think almost all of them will tell you that there's strong evidence for inflation, experimental evidence for it, observational evidence, in the form of fluctuation spectrum, the spectrum that's necessary to describe evolution of structure and so forth. Highly successful theory. As I said, the consensus is.
I think there was actually something kind of if you look up the axis of evil in cosmology, it actually indicates, so there's like this thing called the background microwave radiation, or like something to that effect. And basically when you look at the background radiation from like that's left over from the Big Bang, you would think that it would be like you would see like the radiation kind of distributed in like this weird like cone shape to kind of indicate like that there was a singularity like in the far past, and then everything began to like expand outwards, right? So you'd see like a weird concentration, but like what the CMB kind of indicates is like that that we, like the Earth, the solar system, our galaxy is actually like in the middle of all of this shit.
What's
Yeah,
it called?
it's called the axis of evil.
Axis. Okay.
Axis of evil in the cosmological microwave background.
For obvious reasons. I mean, here's the thing. Like, I think they're both plausible. So, like, I mean, we should support it. But of course, he's not going to say anything but the consensus. You know what I mean? Like, that controls whole funding for his pet project. Even if he wants string theory to continue to explore de Sitter space, you see what I mean? He's not going to be helping out his cause if he if he doesn't agree
Yeah.
with the consensus.
That's correct. And they're probably right.
Look, Professor, we can't make an appeal to consensus.
No, we can't.
So, firstly, that's a logical fallacy. I know you know that. And I don't think much science could be done, let alone physics could be done, if we were going to make such appeals. And sure, we can make probabilistic arguments, but your own unconventional views would have been squashed from the starting line if people pointed out that they're probably incorrect as an argument against them. And by the way, Penrose isn't just an offbeat no one. This consensus that you mentioned in theoretical physics, forget about experimental physics, though that's a great point in experimental physics. In the theoretical end, we've already agreed that it's primarily string theorists, which means you're going to get a biased set as a response for anything that has to do with consensus in theoretical
I'm
physics.
glad Kurt
The portion
Jaimungal
of,
was able to
or
address
the
it.
proportion, sorry, of people who believe in
Yeah.
inflation from string theory versus those who don't, there's a disparity there.
Yes.
Even if it's the case that, okay, yes, string theory is not predicated on inflation nor vice versa.
Yeah, I would say most of the string theorists I know, not completely. I think Qumran Vatha sits on the fence about it. But
Gross also believes that inflation, or at least the multiverse that comes from inflation, is of a different sort of not experimentally accessible or unfalsifiable hypothesis, because it's an in principle unfalsifiable hypothesis, unlike atoms of the past, when in principle you could verify atoms with enough precision. But David Gross says that he doesn't like the multiverse.
400 BC, when the atomic theory was first put forward, that was exactly the complaint against it. This is unverifiable. They're too small. We'll never be able to see them. So when quark theory came out, everybody said quarks are confined. We'll never be able to see them. They're unverifiable. What's unverifiable at one time becomes verifiable when technology improves to a point where it can be seen. So will we be able to do the kind of ultra-precise experiments that might be able to detect some things about eternal inflation? Maybe. An example, the flatness or the non-flatness of space. Not space-time, but space. Eternal or the current theories of landscapes and Coleman-DeLucia instantons, whatever, the picture of this landscape filling up with lots of stuff has a prediction. It predicts that space is negatively curved as opposed to positively curved. At the present time, I think to about 1%, we know that space is flat. That's kind of like saying the Earth is flat, because if we look only at a small region within a couple of miles of where we are, it'll look very flat. But if we look out further, in particular, if we look out past the horizon, what Christopher Columbus was supposed to have looked at. He looked out at the sea and to the horizon, look out a little past that. If he could, maybe he'd just get high up on a ladder and see a little further. He would discover that the Earth was round, positively curved. The same thing here. If we can do better experiments, we may discover that space is curved. Not locally, but globally. If the space came out to be